Welcome to the presentation of the effect of increased body motion in virtual reality on a placement retrieval task by Arnaud Prouzeau, Michael McGuffin, and myself, Thibault Friedrich. We worked on how to improve user interfaces for knowledge workers. In virtual reality, you can replace physical desktop monitors with virtual floating windows. It allows users to work in standing mode, sitting mode, or even while moving around. But because of so many windows around, the user may be lost. In the literature, a lot of factors are improving spatial memories of Windows layout. But there is no literature about user locomotion to improve spatial memory of Windows layout in virtual reality. That's why we decided to focus on this specific point. In the literature, various tasks exist to measure the impact of different factors on spatial memory. For example, the placement retrieval task called Data Mountain proposes to the user to place several windows and then retrieve some of these windows. This task has been designed by George Robertson in 1998. And for example, Andy Cockburn used this same task, Data Mountain, to show the impact of spatial memory in 2D and 3D physical and virtual environments. In the literature, you also have the impact of locomotion on spatial memory with wall displays, with, for example, Tsal New that use wall display to show the impact of locomotion on a classification task, or the article of Michael Jacobson, or even the article of Evan Johnson that use wall display to show the effect of locomotion using the same Data Mountain task. And what about spatial memory in virtual reality? Eric Krakos showed the impact of immersion on recall using the principle of virtual memory palace. But there is no previous studies of impact of locomotion on spatial memory in virtual reality. Maybe because it was not easy to create experiments with locomotion in VR in the past. But now, using new VR headset like Oculus Quest, it is far easier. Our experiment consists in a placement retrieval task similar to Data Mountain but adapted to virtual reality. The first phase is the placement of 60 windows, where the user has to drag and drop these windows using an Oculus Touch. Then the user can freely reposition all windows during the phase. The 60 windows were chosen from a pool of 341 screenshots of windows generated from a list of the top 500 websites. The second phase is a browse recall of 20 windows, where one window is displayed to the user and the user has to retrieve the matching windows in the 60 windows previously placed, using a recast selection with the Oculus Touch controller. The Windows content is this time hidden and the user has only one attempt by window. The third phase is a very visible recall of 20 windows using the same recast selection. This time the window content is visible again and the user has several attempts for each window. Our experiment has two main conditions about the movement during the placement phase. The first condition is stationary, where the user can't move outside a virtual disk of 30 cm radius. As you can see on the video, as soon as the user head is outside the disk, the drag and drop is disabled. The user has to come back in the disk to have the drag and drop enabled again. The second condition is locomotion, where the user has to place the window outside a virtual disk of 140 cm radius. As you can see on the video, the window has a red border that disappears as soon as the window is outside the disk. Our experiment gathered 16 participants, 14 men, 2 women, aged between 20 to 36 years old. Given the number of conditions, the number of participants, and the number of windows, we had around 2,000 windows positioned and 1,000 windows recorded. We also measured the time and the error as a distance between the selected windows and the correct windows, using different distance measures like the Euclidean distance, the normalized Euclidean distance, and the number of items closer to the correct one. During our experiment, half the users started with the locomotion and half of them started with stationary. You can see there the layout of this of the participants during the experiment. During our analysis, we use confidence intervals instead of null hypothesis significance testing and p-values based on Pierre Dravicevich's article. About the placement, we can see that the confidence interval of stationary minus locomotion is mostly below 0. It means that stationary is faster than locomotion, but this part is totally normal because user has to use his legs. The real question is, does locomotion improve spatial memory despite this initial time cost? About the visible recall, we can see that there is little or no evidence of difference in time between the conditions. Then we analyzed the error. Based on the confidence interval, we can say there is no evidence of difference between stationary and locomotion in the Euclidean error distance. However, there is a difference using the normalized error distance. But we realize these measures are misleading. In the locomotion condition, windows placed adjacently will automatically have a smaller normalized error distance. So we had to go for post-hoc exploratory data analysis. We used a new way to measure the error distance, which is the number of items closer to the correct one. Following this new distance, the confidence interval stationary minus locomotion is mostly above 0. So we can say that locomotion results in small errors. In conclusion, we can say that locomotion resulted in a modest benefit to spatial memory. However, it increased the placement time of 3.4 seconds per windows. In some cases, indirect input like redcast pointing, for example, is more convenient to position windows, and the lack of locomotion shouldn't substantially harm retrieval performances. Thank you for your attention.